Lewis structures play an important part in determining the shape of a molecule, as it is the central atom and what's surrounding it dictates where the bonds and lone pairs actually arrive in three-dimensional space. And this can be one of the dangers of a Lewis structure. It represents a three-dimensional molecule on a two-dimensional surface. So don't take for granted that what you're looking at on your paper is going to be what is the real shape in 360-degree space. So how do molecules determine their shape? Well, again, it's based off of how many areas surround the central atom. That is, what's inhibited by bonds and what's inhabited by lone pairs. Each lone pair and bond seeks to get as far away from each other as possible, as these are areas with negative charge in them, bonding and lone pairs. They're filled with electrons, so they naturally seek to find an area that's as far away to minimize that repulsive force as possible. We refer the areas around a central atom as electron domains. And electron domains are areas with electrons in them, but it doesn't matter how many electrons are in them. An electron domain can be a double bond or a triple bond. It can be a lone pair or a single bond. Again, it's not important how many electrons are in that region, just how many regions there are. The central atom in this molecule is surrounded by 4 domains: 2 single bonds, 1 double bond, and 1 lone pair. So we would say this geometry is based off of 4 electron domains. And this is what valence shell electron pair repulsion theory is about. It's basically saying how far away can we place all these negatively charged areas so that they minimize their interaction with each other, also referred to as VSPER theory. So when it comes time to predicting shapes of molecules, we have 2 terms we have to consider. We have to consider the electron domain geometry itself, which is simply named after how many areas are filled with bonds and lone pairs. And then we'll also have the actual molecule name itself. Electron domains can range from anywhere between 2 and 6 regions of space surrounded by the central atom. Recall that regions of 5 and 6 domains, they follow under the exceptions to the octet rule. So when you have a Lewis structure, all you have to do is just count around the central atom and see how many regions of space are inhabited by lone pairs or by bonds. That will dictate the electron domain geometry. However, the actual geometry of the molecule is based off of the electron domain, but it has a much more specific title to describe just exactly how many areas have bonds and lone pairs in it. So the electron domain geometry is often not the shape of the molecule, but there are instances where it can arise. The molecular geometry is defined by the position of only the atoms in the molecule and ignores the lone pairs or non-bonding pairs of electrons. Within each electron domain, there may be more than one molecular geometry. For example here, these 3 shapes are all based off of 4 electron domains, but each molecular geometry, tetrahedral on the left, trigonal pyramidal in the middle, and bent on the right, are all based off of how many of those domains are filled with bonds. So let's briefly go over the different names. If you have an electron domain geometry with just 2 domains and they're both bonding, then you have a linear geometry. If you have 3 domains and all 3 of those domains are filled with bonds, you have a trigonal planar geometry. In the trigonal planar geometry, the bond angles are approximately 120 degrees. Make sure you note that, as you will be held accountable for bond angles. If 2 of the domains are filled with bonds and 1 is a lone pair, you will have what's known as a bent structure. This bent structure has a bond angle of 120 degrees, but we'll see in a minute that we can also have a bent structure of slightly less than that. When it comes time to describing the bond angles, like I said, you have to know them, you just have to memorize them. There are things that can add slight variances to the idealized bond angle. One of those being non-bonding pairs of electrons, or lone pairs. Lone pairs sit closer to the central atom than the bonds, which extend quite a far distance out into space, and so lone pairs have the effect of shortening the bond angles on the actual bonding atoms. The more lone pairs, the greater the shrinkage. You can see in the three structures below that as we add increasing number of lone pairs, the bond angles decrease. Likewise, a double or triple bond can cause bond angles to change slightly as well. The degree at which the bond angle changes from a double bond or a lone pair is beyond the scope of this class, and we should really focus on ideal bond angles and not try and memorize each individual bond angle there is, because in different molecules, you can imagine there's different contributions to it. When we have 4 electron domains, we have what's referred to as a tetrahedral domain geometry, and if all 4 of those domains have bonds on them, we have a tetrahedral structure. If 3 of the 4 domains are bonding, then we have a trigonal pyramidal structure, and this is the first time where you can get into trouble with your bond angles from a Lewis structure. If you were to draw a tetrahedral on a piece of paper, you'd probably look and say, oh, gee, all these bonds are 90 degrees apart, when in reality they're 109.5. Trigonal pyramidal is the same thing. They're all about 107, but again, just remember 109.5 and you'll be fine. If you have 2 bonding domains and 2 non-bonding domains, you have another bent structure, this time with a bond angle of 109.5, slightly less than that, but again, don't worry about that too much. Then we get into exceptions to the octet rule. So the next electron domain, we have 5 domains where there are bonding or lone pairs. And we have 2 positions which are on an axis, known as the axial position, and we have 3 atoms in an equatorial position. That is, it lies along an equator if we were to imagine that the atoms were falling on the sphere of a globe. So we'll have to be able to identify axial and equatorial positions in molecules. Now, when we have to put a lone pair on a trigonal bipyramidal structure, we have a choice to make because there's 2 different bond angles. There's the 90-degree bond angles from axial to equatorial, or there's the 120-degree bond angle between equatorial and equatorial. When placing lone pairs on trigonal bipyramidal structures, always place the lone pair on the equatorial position first. All lone pairs take equatorial positions before they will take axial positions. In this trigonal bipyramidal electron domain, we have its 4 distinct geometries. We have a trigonal bipyramidal, which is when all 5 domains have bonds in them. We have a seesaw when we remove one of the equatorial positions. We have T-shaped when we remove 2. And we have linear when we remove all 3. Likewise, when we have an octahedral electron domain, that is 6 bonding domains, we only have 3 structures we can describe. We have the octahedral, when all 6 positions are occupied with bonds. Then we have square pyramidal, when we take off one of the bonds and replace it with a lone pair. And on the picture there, you might be asking why they put it on the axial position. Doesn't really matter because all the bond angles here are 90 degrees. So it's only the trigonal bipyramidal structure you have to worry about that lone pair. But when you remove a second bond in the square planar shape, you always have to take the bond away from the opposite side of the lone pair so that the lone pairs are always 180 degrees apart from each other. When it comes time to describing atoms with more than one central atom, we have to describe each individual central atom in terms of its geometry. That is, these 3 structures over here on the right, there's no one geometry that fits it. Rather, each central atom has its own geometry to it. And so that is how we have to label and describe individual atoms, central atoms, in molecules.